So hello everyone to chapter 11 of Chemical Structure and Reactivity, brought to you by me, Palladium. And right here's the shout-out list and also the YouTube list. So, heartfelt thanks to everyone that helped support these lectures, that these lectures will be official CODS lectures instead of guest lectures. But let's talk about this chapter, right? Chapter 11 of Chemical Structure and Reactivity. So, this chapter is the first chapter in this book, which covers organic chemistry. So in this chapter, we will focus on what are known as functional groups. So these functional groups are present within organic chemistry, and it's basically an area within like an organic molecule. All you need to know, functional groups are areas within organic molecules that contribute to chemical properties and also help contribute to the reactivity of a molecule. Now, here are some key points that you should understand by the end of this chapter. So our first key point is we can classify these functional groups. So just as I said, functional groups are areas or certain regions of a molecule that give certain properties or certain or contribute to the reactivity of the molecule. Now we can categorize these functional groups based on the number of bonds that are created from a carbon and another atom that has greater electronegativity. Reactions can also be classified by looking at how the functional group level changes. So, functional groups and functional group levels mainly constitute these first 2 points. Now, our third point here is that the outcome of a reaction can be rationalized. So, what does rationalized mean, right? So, rationalized is you give your own rationale for something. So, you give reasons, you build like some kind of proof. So, using our knowledge of homoluminal interactions, which I talked about back in chapter 10, we can rationalize the outcome of a reaction. Now, our fourth point is that there's a general order of reactivity with various functional groups at a certain level. So some functional groups, some like level 3 functional groups, will be more reactive than other functional groups. And our final point is that transformations that can change functional group level will depend on a lot of factors, like the reactants or reagents that are used and also the environment. So some of the reactants we'll be focusing on will be like reducing agents, oxidizing agents, nucleophiles, and the environment could be like basic or acidic. So here are your first steps into organic chemistry. So this is the first year college textbook. Organic chemistry is the study of carbon-based compounds. And back then, this field of study used to be restricted to chemicals that came from biological systems. So that's why it was initially called organic chemistry, because it came from organisms. Now, this was fine and all, until we have this German guy, Friedrich Wöhler here. He created urea, which is, guess what, found in urine. And he created it from ammonium cyanate. And ammonium cyanate is an inorganic compound. So then that definition of organic chemistry got broadened in study of carbon-based compounds. So in the organic chemistry world, a lot of effort is put towards improving what is known as organic synthesis. So organic synthesis is just like, how can I create this desired molecule from this molecule, right? And we have entire people devoting their lives to this cause. If you've been in the server, you know people like Abhishek and Jane Nasty. They spend a lot of their time doing organic synthesis. Now, here's a fun fact about organic chemistry. It's also used, but one of the reagents in organic chemistry can be palladium. And actually, palladium is often used in catalytic car converters, so that's just a fun fact. Now, let me give you guys an introduction to functional groups. So, as I said in the beginning, functional groups are sections within an organic molecule that give those certain chemical properties, right? So right here are a bunch of functional groups. So I got this image from Master Organic Chemistry, which is a great website. I recommend trying it out. So you have stuff like an alkane. So alkane is just a hydrocarbon with single bonds. Alkene has a double bond. Alkyne has a triple bond. we have benzene rings, amines, alcohols, which is hydroxyl group, ethers, which is an oxygen connecting two R groups. By the way, R just means rest of the molecule. And we have stuff like alkyl halides, which is just like an R group attached to a halogen. Thiol, which is like an alcohol but with sulfur instead of oxygen. Aldehydes. Aldehydes basically, if you have a carbon atom and it's double bonded to an oxygen, and it's also bonded to an R group and an a hydrogen. Ketone is basically the same thing as aldehyde, but that hydrogen is replaced by another R group. Ester is like a combination of ketone and ether, in that we have a carbon that is both doubly bonded to an oxygen and singly bonded to another oxygen. Carboxylic acid, which is COOH, and an amide, which is, in my opinion, a combination of a ketone and an amine. Now, also be wary, aldehydes and ketones are grouped together in the carbonyl group. So carbonyl just means a carbon that's double bonded to an oxygen. So level 1 functional groups has a carbon atom that's bonded to only one other atom of greater electronegativity. Take something like an alcohol, right? So an alcohol has a carbon that has 3 bonds to 3 R groups, but to 1 bond to a hydroxyl group, OH. And since oxygen has a greater electronegativity than carbon, it's only a level 1 functional group. You also have stuff like thiols, peroxides, azides, epoxides. Epoxides are basically rings, ethers, and thioethers. And right here, this is also super important, amines. So amines is basically a carbon that forms 3 bonds to 3 R groups, and it has 1 bond to a nitrogen, and that nitrogen makes 2 other bonds. Now, amines can be split into 3 categories: primary, secondary, and tertiary. So primary is if that nitrogen has only 1 bond to a carbon. Secondary is if that nitrogen has 2 bonds to a carbon. And tertiary is if that nitrogen has 3 bonds to a carbon. So that's classification of amine. Now, here's some more on functional groups. So in the previous slide, I've shown you what level 1 functional groups are. So these have a carbon that is bonded to only one more electronegative atom. If you're trying to draw organic molecules, we often use a thing known as a stick/skeletal structure. And basically, what this does is it puts less emphasis on that carbon frame, because in organic molecules, there are a bunch of carbons, right? So there are carbons left, right, and center. And here's some more on functional groups. Other than double and triple bonds between carbons, the functional groups of an organic molecule can include the heteroatoms, which are atoms that are not carbon or hydrogen. And these are because heteroatoms like oxygen, sulfur, or nitrogen, they can have high energy lone pairs, and in addition, they can form lower energy vacant antibonding molecular orbitals. So that was a mouthful to say, but just know that heteroatoms have high energy electrons, and because they have high energy contributions, they can attack other molecules. And the lower energy vacant antibonding molecular orbitals, because the LUMO is lower in energy, that means that there'll be more reactivity, because homo-LUMO interactions are the base of organic chemistry. So next, I want to go over some more on functional group levels. So as I said before, we can categorize certain functional groups by looking at how many bonds are created between a carbon atom and some other atom that has greater electronegativity. So the heteroatoms that we'll consider in this chapter will include oxygen, sulfur, nitrogen, and halogens such as fluorine and chlorine. And also right here on this bottom part, we can see that there are a bunch of reactions. So this is known as an alkyl halide. And an alkyl is basically like if we take off like one hydrogen off an alkane, right? So an alkane is just a hydrocarbon with single bonds. Pretty boring, right? An alkyl halide is basically what if we took a hydrogen off that alkane and replace it with a halogen. So right here are a number of the transformations that can go with level 1 functional groups. So for example, if you put something like base in, like sodium hydroxide, those hydroxide ions will substitute themselves for the bromine atom in bromobutane. So that's enough on level 1 functional groups. Let's go on to level 2 functional groups. So right here are the carbonyls, okay? So ketone and aldehyde. So ketone, we have a carbon that's double bonded to an oxygen. Aldehyde, carbon that's double bonded to an oxygen. But here's the thing. In the ketone carbon here, this one highlighted in red, also forms 2 bonds with 2 other carbons. But with the aldehyde, the carbon forms a bond with R, which is just the rest of the molecule, but also, a hydrogen. So generally, you'd find aldehydes at the end of carbon chains and ketones at the middle of carbon chains. So next I want to go over the level 2 functional groups containing hydrogen. So these are known as imines and oximes. So amines consists of a carbon that forms 2 bonds to 2 R groups, but it's also double bonded to a nitrogen atom, and this nitrogen atom also forms a single bond to some R group. Now an oxime is basically the same thing as an amine, but that R group that nitrogen is bonded to is replaced with OH, which is hydroxyl group. And then we have all these. So these will be pretty important soon. So this is known as a hydrate. So in a hydrate, carbon forms 2 bonds to 2 hydroxyl groups and 2 bonds to 2 R groups. And acetal, also sometimes called a ketal, is formed when you have a carbon that forms 2 bonds to Cr3 groups, so 2 bonds to 2 carbons, but also 2 bonds to oxygens, and those oxygens are attached to carbons. So this functional group here is also called an acetal, but you can see how this quote-unquote ketal, in this acetal, we have the Cr3, is simply replaced with a hydrogen atom. So acetal and acetal, but this is also called a ketal. So for some reason they're both called the same, I don't know why. So next I want to go over what hemiacetals are. So hemiacetals is basically when you have a carbon that forms 2 bonds to 2 R groups, 1 bond to a hydroxyl group, and also another bond to another oxygen here, and that's bonded to a carbon. So hydrates, acetals, quote-unquote ketals, the real acetal, and hemiacetal. This will be important soon. And next out, this last one is known as the gem dihalide. It's basically a carbon that forms 2 bonds to halogens. So here's the second part of level 2 functional groups. So, for level 2 functional groups, right? That carbon atom in the organic molecule could have a double bond to an atom of greater electronegativity. Take, for example, ketones. Ketones have that carbon double bonded to oxygen, which is of a greater electronegativity, but that carbon can also form 2 single bonds. For example, in a gem dihalide, it forms 2 single bonds to 2 halogens. So in the later section of the chapter, we will focus on 2 functional groups, hydrates and hemiacetals, which are formed from the reaction of a carbonyl group with either water or an alcohol. So remember, an alcohol is basically just R, some group R that's bonded to OH. So compounds containing these, like hydrates and hemiacetals, can only exist in solution, and you really can't isolate them, because that would mean that that original carbonyl, that would be reformed, right? And also that alcohol/water will be reformed. So you really can't isolate it. So right here are level 3 functional groups. So this one is known as the carboxylic acid. It's C double bonded to O and also bonded to a hydroxyl group. And you can see it's also bonded to an R group. An ester is almost the same thing as carboxylic acid, but that oxygen that's singly bonded to that carbon, instead of being also bonded to a hydrogen, is bonded to another carbon. So next I want to go over an amide. So amide has a carbon that's double bonded to oxygen and has a single bond to a nitrogen, which has 2 R groups attached to it. And I want to go over what an acyl chloride is. So an acyl chloride is, we have a carbon here, it's bonded to some other group R, it's doubly bonded to an oxygen, and also has a single bond to chlorine. Acyl chlorides will become important in the later parts of this chapter. So right here, this is known as an orthoester. So this carbon makes 3 bonds to oxygens, which are all attached to carbons, and also 1 bond to an R group. Next, then we have the trihalide, which is a carbon that is bonded to 3 halogens through single bonds, and also bonded to 1 R group. So X in these functional groups generally represents a halogen atom. So next, I want to focus on cyanide/nitrile. In this chapter, we'll focus on calling it nitrile more. So that carbon atom is triply bonded to nitrogen, but also has a single bond to this R group. And finally, we have an acid anhydride. So basically, think of if we have these 2 carboxylic acids. If we have like 2 carboxylic acids, right? If we remove a water molecule, then we will end up forming this acid anhydride. So we have 2 carbons here, they share an oxygen atom, and they're also each doubly bonded to another oxygen. So those are your level 3 functional groups. And that's as far as we can practically get. There are level 4 functional groups. So here's some other notes on level 3 functional groups. Most of these contain a double bond between a carbon and an oxygen, and the carbon also being bonded to one other electronegative atom. But it is possible to have just a triple bond or 3 single bonds instead of just a double bond and a single bond, as shown with the nitrile group or trihalides. And finally, we have level 4 functional groups. So generally these are more unstable. So we have carbonates, we have that carbon, double bond to an oxygen, and 2 single bonds to 2 oxygens here. Orthocarbonate is just that carbon makes bonds with all oxygens, and all of those oxygens are bonded to carbons. And then we have a carbamate, which is basically like a carbonate, but we replace one of the oxygen atoms that's singly bonded with carbon with a nitrogen atom. And that nitrogen atom bonds to hydrogen because of formal charges. Next, we have the isocyanate. So we have the carbon here, and it's doubly bonded to nitrogen and doubly bonded to oxygen. And that nitrogen then is bonded to an R group. And finally, we have our substituted urea. Functional groups can be very easily hydrolyzed. So take, for example, something like orthocarbonic acid, right? So we have a carbon here, bonded to 4 oxygens, and each of these oxygens are attached to a hydrogen atom. It can be easily hydrolyzed to form carbonic acid, and then we can form carbon dioxide with it. So right here is this what I like to call the transformation zoo. So we have a bunch of level 2 functional groups, and here are many of the transformations that it can go under. So we have stuff like gem dichlorides, so we have that carbon here with 2 bonds to chlorine. We have acetyls, oxines, imines, and also the ring form of glucose, which can be considered a hemiacetal. So we have like acidic conditions, just water, glucose in equilibrium with water, a lot of transformations. So right here are our level 3 functional groups and the amount of transformations that it can go under. So we have esters, acid anhydrides, trichlorides, and nitriles. And we can put them under acidic conditions. We can use things like phosphoric acid, or just put an acid anhydride in water. So here are just a few transformations. That's all cool and all, identifying the functional group level. Like, oh my god, this carbon forms like 4 bonds with oxygen, right? But how can we change the functional group level? Because that's a way that we can actually, categorize. So there are 3 things that we can use to change the functional group level depending on what you're looking at, right? So reducing agents, guess what? Reduce the functional group level. Oxidizing agents will increase the functional group level, and a carbon nucleophile will help form a new carbon-carbon bond. Now, keep in mind, you can't just put some organic molecule with a reducing agent or an oxidizing agent and hope that this will all be fine. Most of these organic reactions contain many steps within them. So it's really a complicated process, and that's why people devote their whole lives to, the world of organic synthesis, just how complicated it is. And see, I remember there's this one thing called the Suji-Trost reaction. It's a lot. Anyways, first I want to go over reducing agents. So there are 3 reducing agents that you'll need to know for this chapter. LiAlH4, which is lithium aluminium hydride, sodium borohydride, which is NaBH4, and DiBalH. DiBalH stands for diisobutyl aluminium hydride. It's a lot to type. So just know 3 reducing agents: lithium aluminium hydride, sodium borohydride, and DiBalH. So first I want to go over carbon nucleophile. So second I want to go over carbon nucleophiles. So if we want to replace the bond between the carbon atom and electronegative atom with a new bond between carbons, we can use something like a nucleophilic carbon. So we have many available, like cyanide. So nucleophilic, that means positive loving. So the cyanide ion is negatively charged, so of course it's going to love positive charge. So therefore it is a carbon nucleophile. We also have things like organolithium reagents and Grignard reagents. So organolithium reagents consist of a carbon-lithium bond, and Grignard reagents consist of carbon that's bonded to magnesium, and that magnesium is also bonded to a halogen atom. So using a carbon nucleophile to replace the bond between a carbon and a more electronegative atom will, in the end, lead to the functional group level being lowered. So here are a few examples of carbon nucleophiles in action. So if we take something like, this is known as propanone, so this is a ketone. If you put something like sodium cyanide in it, that cyanide ion will be nucleophilic. So it will try somewhat breaking that double bond between the carbon and the oxygen. And we can see that the cyanide ion attaches itself to that central carbon and reduces the functional group level from 2 to 1. We also have organolithium reagents right here, and you can see we can reduce that functional group level from 2 to 1. We also have our Grignard reagents here, so we have magnesium that's bonded to carbon, and that's also bonded to a halogen. And right here we can stick new substituents onto a carbon, and we can thus reduce that functional group level. Now keep in mind, after using organolithium reagents or Grignard reagents, you will have to subject the molecule to acidic conditions. This means adding things like sulfuric acid into solution. So finally, I want to go over oxidizing agents. So some examples of common oxidizing agents in organic chemistry. If you've taken IB Chem before, you should know this. Are PDC, which stands for pyridinium dichromate, potassium permanganate, KMnO4, sodium dichromate, Na2CrO7, and lead tetraacetate, which is known as PbACO. And if you see abbreviations like AC or ET, sorry for mentioning this, if you see abbreviations like PH, AC, or ET, those generally denote benzene rings, like ethyl groups, methyl groups. So here are a few oxidizing agents in action. So the process of oxidation will depend on what agent you pick. So what this implies is that some oxidizing agents will be harsher than others. So right here we have 2 examples. These are known as primary alcohols. And the reason for that is because that carbon that's bonded to oxygen is only bonded to one other carbon. So it's known as primary alcohols. So we can use oxidation agents to raise that functional group level. If we use something like pyridinium dichromate, PDC, then what will happen is we'll raise that functional group level from 1, which is alcohol functional group level, to 2, and we get an aldehyde. But if we use something like potassium permanganate, then in the end we will get a carboxylic acid, which raises the functional group level from 1 to 3. So this just goes to show how some oxidizing agents can be harsher than others. So here's an important note for you. Reaction steps. So many of the reactions that we will cover occur in multiple steps, like for example the reduction of carbonyl group. So each step will have to follow the last step. So remember that, follow. So we simply cannot put lithium aluminium hydride in solution and then acidic conditions at the same time. That just wouldn't work. So the notation above signifies that the ketone is first reacted with lithium aluminium hydride, and then aqueous acid is added. So we have this reaction, the reduction of our carbonyl group. So lithium aluminium hydride comes first, and then we add aqueous acid, which is acid in water solution. And the second part of the reaction is known as a workup. So right here is a summary of basic transformations. So reactions are generally centered on the heteroatoms in an organic molecule because they produce lower energy LUMOs and they have high energy electrons. And apart from pi bonding between carbons, the overall carbon framework mostly stays the same in an organic reaction. So pi bonding is like the overlap of p orbitals, and in chapter 15 we'll focus on the reactions of pi systems. So we're going to focus on aromatic compounds and whatnot. So our third point is the functional group level is the number of CX bonds that are formed. So X is just an atom with greater electronegativity. And in the presence of excess water, maybe acid base, most level 1 functional groups will be hydrolyzed to form primary alcohols. Most level 2 groups will form ketones or aldehydes, and most level 3 groups will form carboxylic acids. And for most level 4 groups, we'll just create carbon dioxide. So our final point here is that moving down a functional group level will require the use of a reducing agent, while moving up a functional group level will require the use of an oxidizing agent. That's a summary of your basic transformations. So let's first focus on level 2 to level 1 transformations. This is known as carbonyl addition. So the simplest reaction that we can happen is known as the nucleophilic addition to the carbonyl group. So right here is the overall reaction. So we have our carbonyl group here. We have some nucleophile X minus, and using curly arrows, we can sum up the reaction. So we get a new CX bond, but there's also a redistribution of electrons from that pi bond formed between carbon and oxygen, and that's redistributed back to a lone pair on the oxygen, which gives it a negative formal charge. So one example of the nucleophilic of the carbonyl group concerns the formation of something known as acetone cyanohydrin. So this is how we form it. So acetone cyanohydrin is, we first get acetone, and we form it with the reaction of acetone with both hydrocyanic acid, HCl, and potassium cyanide. So potassium cyanide is soluble. So we're just going to get cyanide ions in solution. And you can see that cyanide will attack the carbon, and our pi bond between carbon and oxygen is redistributed to a lone pair. So we get this tetrahedral intermediate, and that oxygen gets a proton from hydrocyanic acid, and in the end we get acetone cyanohydrin. And here's an industrial application of it. So this can be used as a source of the cyanide ion. It can be very easy, because if you put it in base, right, according to the Arrhenius definition, a base such as sodium hydroxide will produce hydroxide ions, and this will deprotonate the OH group, and because this oxygen is negative, the cyanide bonded to the carbon is pushed out and acetone is reformed. So if you put this in base, we'll get this tetrahedral intermediate, and this will just go back to acetone and the cyanide ion. So next I want to focus on how we can form these things known as organometallic reagents. So organometallic reagents in the name contain a carbon-metal bond. In fact, organometallic chemistry is actually very interesting. So many metals are used for organometallic reagents, such as copper, palladium. In this section, we'll focus on two kinds of organometallic reagents. Organolithium, which implies a carbon-lithium bond, and Grignard reagents. Grignard is basically just, he was a really great French chemist, and he discovered these reagents. So the formation of an organolithium reagent is you have 2 moles or 2 equivalents of lithium plus 1 equivalent of R bonded to something X, and that X could be like chlorine, and then we get R bonded to Li plus Lix. And the formation of Grignard reagent is Mg plus Rx is equal to Mgx plus R, and X here is the halogen atom, because Grignard reagents have a carbon-magnesium bond, but that magnesium is also bonded to a halogen atom. So here are a few examples of important organometallic reagents, so you can bag these off of Sigma Aldrich. So we have things like methyl lithium. So that's just CH3, and that carbon is bonded to lithium. We have ethyl lithium, phenyl lithium, phenyl magnesium chloride, so this is a Grignard reagent. We also have probomagnesium chloride, which is another Grignard reagent. And you can see these are our important organometallic reagents. So organolithium and Grignard reagents. So right here, I'll talk about bonding within organometallic reagents. So the simple structures that I showed you, right? These very simple skeleton stick structures, they're sort of misleading. So organometallic chemistry is a bit tricky, because something like ethyl lithium can actually form tetramers, so it can kind of polymerize, sort of. But the important thing, in the end, with bonding in organometallic reagents is that that carbon-metal bond is very polarized. So that carbon will have a partial negative charge, and the metal will have a positive partial charge. And this, in the end, will lead to that sigma bonding molecular orbital to be higher energy. And because we have those high energy electrons, that means that we can use organometallic reagents like carbon nucleophile. So if we use something like an organometallic reagent on the carbonyl group, those high energy electrons from the carbon metal bond can go into that pi anti-bonding orbital formed between carbon and oxygen, and then it will break up that'll break up that pi bond between carbon and oxygen, and it will form a new bond. And we get this thing known as an alkoxide here. And we have a metal cation, and we have an oxygen. We have an oxygen with a negative formal charge. So what we do is we'll need an acid workup in the end. And from this reaction as a whole, with organometallic reagents and the carbonyl group, that CO bond becomes that CO double bond just means that now there's a carbon that's bonded to an oxygen, which is just bonded to hydroxide. So the carbon is bonded to a hydroxyl group, and we also have that R section. We just have R also bonded to the carbon group. So right here are a few examples of organometallic reagents and their reactions. Yeah, take for example B here. So 1, 2, 3, 4 carbons. So using our organometallic reaction, we can see this ketone. You see that the carbon is now bonded to a hydroxyl group. That original methyl right here is redistributed here. And we also have this N-butyl group also bonded to the ketone carbon. So these are a few examples of organometallic reagents. I want to go over metal hydride reducing agents. So we can reduce aldehydes and ketones with reducing agents, namely lithium aluminium hydride, LaAlH4, and sodium borohydride, which is NaBH4. So, from the general knowledge that's collected from this book, we can say that there's a singly charged metal ion, which is either like Li plus or Na plus, and we have these anions that are singly negatively charged. And the central atom in both each of these anions are sp3 hybridized, even though hybridization is fake. So, this will be useful for considering the reactivities of the reducing agents. So, let's talk about the reactivity difference between lithium aluminium hydride and sodium borohydride. So generally, lithium aluminium hydride will just reduce a lot more compared to sodium borohydride. And that is because there's a greater energy mismatch between the sp3 orbital of aluminium and the 1s orbital of hydrogen. But if you compare that to the energy mismatch between the sp3 orbital of boron and the 1s orbital of hydrogen, there's not as much as an energy difference if we use boron instead of aluminium. So that means that the aluminium hydrogen sigma bonding molecular orbital is now higher in energy, which means that lithium aluminium hydride will be more reactive. In fact, here's a fun fact. If you put lithium aluminium hydride in water, you will undergo like a super violent reaction. It'll form hydrogen gas, will be very violent. But sodium borohydride will only slowly fizz with water. Will slowly react with water. So right here's an example of how we can use a reducing agent, which is sodium borohydride, for the reduction of a carbonyl. So in the first step, that LUMA of the aldehyde or ketone is first attacked by the high energy electrons from that boron hydrogen bond, and this will form an alkoxide. So we have borane left here, and we have alkoxide ion, and we have this positively charged metal ion. So what we will then need is an acid workup to reprotonate or to protonate this negatively charged oxygen. So in the end, we can see with this carbonyl carbon, it will now be bonded to a hydroxyl group instead of double bonded to oxygen. It will also form single bond to a hydrogen. So that's the overall reaction. So here's the thing. Unfortunately, the reaction seen here is somewhat of an oversimplification, because that alkoxide can donate electrons to the borane. And so that new molecule can act as another reducing agent, which can be hydrolyzed to form the alcohol. So this is kind of like a bit of misleading, because it kind of underestimates how we can get some kind of chain reaction from the reducing agent. So we also have other reductions. So it's also possible, so this is not going to be carbonyls, we can reduce the pi bond between carbon and nitrogen and imine with either sodium borohydride or lithium aluminium hydride. And you could think of this as being similar to the reduction of a pi bond between carbon and oxygen. However, here's the thing. If we're using something like sodium borohydride in solution, then it's necessary that's in a solution of methanol alcohol instead. And in acid, it will be protonated. So we'll get back to the use of these reducing agents later. So namely, it will be in other level functional groups. So next I want to focus on another transformation, which is the formation of hydrates or hemiacetyls. So hydrates is basically, if you have an aldehyde in water, we have a hydrate form. It's also known as a geminal diol. But if we have an aldehyde in alcohol, a hemiacetal is formed in equilibrium. So here's the curly arrow mechanism that we can use instead of a bunch of MO theory for forming hydrates. But flashbang, we still get MO theory. So with these reactions, the high energy lone pair of the oxygen in either the alcohol or water molecule attacks the pi antibonding LUMA of the aldehyde. So you can see it kind of attacks that, and we have a positively charged oxygen here and a negatively charged oxygen. So it's forming a hydrate. And we have this proton transfer step. So this kind of seems like we can just take one hydrogen from this one oxygen molecule and stick it on this other hydrogen, right? But that's not true, because if you remember back in chapter 1, right, I focused on intermolecular forces, and hydrogen bonding was one of them. And some of these hydrogen bonds can be so strong that we get new bonds. And so this proton transfer step is kind of an oversimplification, but the protons don't actually just get swapped around. They get attached to the oxygens from hydrogen bonds. Now, if you look back, right, you can see that we have these equilibrium harpoon arrows, right? So we need to focus on the equilibrium, because flashbang here, some aldehydes will form more hydrate than other aldehydes. So there are two factors. If we have something like an electron withdrawing group near that carbonyl, near the aldehyde carbon, right? So if you have something like fluorine bonded to the carbon, we will increase the amount of hydrate slash hemiacetal that's present. And in addition, in the aldehyde, if we have a larger size group R, then the amount of hydrate slash hemiacetal decreases. So right here is a table that shows you the percentage of hydrate in aqueous solutions of aldehydes, right? So right here, this is methanol slash formaldehyde. So it's 99.95. That's a percentage of hydrate. But you can see if we include more carbons that are bonded to that aldehyde carbon, that R group gets bigger. The percentage of hydrate all the way goes down to 20%. Here's the issue. Okay, there's an issue with hydrates and hemiacetal. So they're cool and all, right? But you can't really isolate them, because if we try to do that, then simply that original carbonyl and the water slash alcohol molecule will be reformed. So I have just the solution. Acetals are formed from the reaction of a carbonyl group with alcohols and a trace amount of acid. And that acid is added because if we can protonate the carbonyl first, that pi antibonding LUMO is lowered in energy. And keep in mind the reactions that form an acetal are all in equilibrium, so they will be reversible. So here is the visual representation on how to form an acetal. So we first have our protonated carbonyl, and we have our alcohol. It's going to attack that pi antibonding LUMO, and then we are going to get a protonated hemiacetal. And keep in mind, yeah, this will happen in equilibrium, so it sometimes can reverse. But assuming that that doesn't happen, then we're going to use a proton transfer here. And we can see here the proton, quote unquote, gets stuck onto that other oxygen atom. This one's called OK. This one's called OA. And in the end, we have B. So what actually can happen is we can use curly arrow mechanisms, and we can see that a water molecule is going to leave. And now we have a carbon that's double bonded to an oxygen, and it's attached to this R prime group. Now, we have compound C. So this gets, again, attacked by an alcohol molecule. And in the end, we get an acetal. And you can see we have that minus H plus that minus proton step. So even though it is a bit hard to memorize, just know if we react the carbonyl group with acid and alcohol, then we will end up forming an acetal, which can be extracted. It should be hydrolyzed in acidic conditions. So, in fact, you can turn that acetal back into the original carbonyl by just adding acid. So the acetal is first protonated, and then we have an alcohol molecule that's just removed. And after that, in a sense, that entire pathway for the reaction is just reversed, and we end up getting the original carbonyl. Before we get into the next section, after the acidic hydrolysis of acetals, I want to discuss some important terminology regarding the functional group carbon. So in a functional group, the carbon is considered primary if it's only bonded to one other carbon. We have secondary compounds, which have the carbon bonded to two other carbons. And a tertiary compound has the functional group carbon bonded to three other carbons. Now, keep in mind, this is the correct terminology for things like an alkyl halide or an alcohol. But for amines, it's different. And for amines, it's determined on how many NH bonds are formed. So, next I want to focus on the reaction between amines and the carbonyl group. So, here is the most uneventful part of this chapter. And if we react a tertiary amine, which has no NH bonds, with the carbonyl, then no reaction happens. All that amine does is attack that pi antibonding LUMO of the carbonyl, and thus just decides to leave. So, genuinely, there's just no reaction. Now, if we react a primary amine and a carbonyl, this is where things start to heat up. Because if we react a primary amine and a carbonyl, we get the formation of what is known as an imine, which is, yeah, of course, better than no reaction. So that primary amine attacks the pi antibonding LUMO of the carbonyl, and then proton transfer occurs, and if we have extra protons, then that OH group will be protonated, which will result in H2O molecule leaving, and in the end we get the formation of an amine. Now, secondary amines plus a carbonyl, okay, this part is kind of tricky, to be fair, because there are two paths as per this chapter that we can take. So you can form what is known as an N-amine from the reaction of secondary amine, which only has one NH bond. And this forms what is known as an aminium cation. And then this will form what is known as an N-amine. So there's a CC double bond. And now we have this hydrogen that's removed here. A hydrogen is removed here, and we also have that CN bond. Here's the second pathway with reacting secondary amines in the carbonyl group. If this is a special case, if you have an aldehyde, and the carbon right next to the aldehyde forms no CH bonds, then this will form what's known as an aminal. So this is our second pathway as per this chapter with the reaction of secondary amine plus carbonyl. Means aldehydes and ketones can still react with many compounds that contain NH2 groups to form what are known as oximes and hydrozones. And you can also hydrolyze gem dichlorides to form carbonyls. Keep in mind that, in the words of our good friend Kuravax, should is a subset of can, which means that some mechanisms, while you can do it, doesn't mean that you should. And I took this directly from the authors. So I want to go over our first level 3 transformation, which is known as the hydrolysis of an ester. So this can happen in two conditions, acidic or basic conditions. In turn, the kinetics, which is analyzing the rates of reactions, the hydrolysis of an ester at a constant pH is equal to K ops times the concentration of the ester. So K ops is just an observed rate constant, and this rate constant will depend on the pH. And you can see this bracket ester is the concentration of the ester. So right here is the chart for a rate constant based on pH. So we have our acid hydrolysis of ester and our alkaline/basic hydrolysis of an ester. So overall, as the pH gets more extreme, then the rate constant will increase more. So here, we're going to focus first on the alkaline hydrolysis of an ester. So, because we have hydroxide ions, high energy electrons from there will attack that pi antibonding orbital between the carbon that was initially double bonded to the oxygen atom. And so we yield an alkoxide ion, and we form a carboxylic acid here. But because, I repeat, because we have hydroxide ions in solution, that carboxylic acid will be deprotonated. This will form our ion here, ethoxide ion. And right here are our relative energies for the alkaline hydrolysis of an ester. So you can see that in the end, this ethoxide ion is at a much lower energy than this original ester in basic solution. And this tetrahedral intermediate right here is highest in energy. Next, I want to focus on the acid hydrolysis of an ester. So, if I can sum up this reaction, then I'll say that the acid-base hydrolysis of an ester will convert it into a carboxylic acid. So, this kind of reminds me of that time we talked over the alkaline hydrolysis of an ester. But that carboxylic acid won't be deprotonated by base, but because there is none. But keep in mind that this is a different mechanism. So this carbonyl is first protonated, and then H2O attacks the pi antibonding LUMO of the protonated carbonyl, forms that tetrahedral intermediate, and then we get a carboxylic acid, which is protonated to that doubly bonded oxygen. In the end, we get a carboxylic acid. So this is the acid-base hydrolysis of an ester. Now, going more on how we can prepare carboxylic acids, we can prepare them from nitriles, which is basically a cyanide group that's bonded to another group R. So the nitrile is first protonated, which has similar effects to protonated carbonyl, and then we have our LUMO here. So our LUMO will just keep getting attacked and attacked over and over again by water, and we will get ammonia as a product, and in the end we get a carboxylic acid. Now, keep in mind we also have the equilibrium arrows. And in addition, if possible, you can also partially hydrolyze a nitrile to form an amide. So here, I want to focus on this sort of reactivity series with carbonyls, okay? The ability for different functional groups to be hydrolyzed in water will be a reflection of how reactive they are. So, remember, keep in mind that in the hydrolysis of these carbonyl groups, right, a lone pair from water will attack that pi antibonding LUMO of the carbonyl. So this will be a reflection of how low the energy of the LUMO is. So acyl chlorides are actually the most reactive, while amides are the least reactive. So in the next slides, we'll go over the reasons for why. And keep in mind, acyl chlorides are the most rapidly hydrolyzed in water. This means that the LUMO is actually the lowest in energy. So I want to focus on esters versus just normal carbonyls, aldehydes slash ketones. So imagine that we first have methanol, which is the most basic aldehyde. So we have pi and pi antibonding orbitals. Now, what if we conjugate another p orbital with both the pi and pi antibonding orbitals? And if we can use the relative energies of the p orbitals and the pi-pi antibonding orbitals, as shown right here, we can determine that the LUMO energy for an ester is actually greater than a carbonyl LUMO. And next I want to go over why amides are actually having their LUMO higher in energy. And that's because the energy of the 2p orbital in nitrogen is greater than the energy of the 2p orbital in oxygen. So if we conjugate another p orbital with the pi-pi antibonding orbitals, then that LUMO will be higher in energy, so it's going to be less reactive on amide. Now, I want to go over acyl chlorides. So, here's the question. Why are acyl chlorides considered the most reactive out of all of these carbonyls, even when there's not much of a difference in orbital energy between the p orbitals of both nitrogen and chlorine? So, the reason for this is because there's actually less overlap between the chlorine and the existing pi-pi antibonding orbitals. So, this is known as hyperconjugation, and this is where you have CH sigma orbitals, and these kind of conjugate with existing pi systems, and this will affect the energy of the LUMO. You can find this in molecules such as propanone. So next I want to go over how we can prepare acyl chlorides. One may think that if we have like a carboxylic acid here, right, then what will happen is we can just react that carboxylic acid with some source of chloride ions like NaCl, and the molecule will, guess what, become an acyl chloride. But if I look at the equilibrium constant using thermodynamics, the equilibrium constant K is going to be super small, right? 1.05 times 10 to the negative 7. That means that reactants are heavily favored in this reversible reaction. So we can't do that. Now, the way that you should prepare acyl chlorides is we use something known as thionyl chloride, which is SOCl2. And if we look at the thermodynamics, we can look that products are heavily favored, as K is equal to 4.5 times 10 to the 10th power. So next I want to go over the ability of leaving groups. So right here we have these different acid derivatives, and we can actually rationalize the reactivity of these acid derivatives using, just like how good are these leaving groups. So, because acyl chlorides are the most reactive, then the chloride ion will be the most reactive. So, ethoxide ion is second best. We have our OR minus group, which is somewhat poor, and NH2 minus, which is the poorest. So, I want to go over next our nucleophilic catalyst. Increase the rate of an organic reaction by replacing a leaving group with another to create a new functional group that's more reactive. So we can use something like pyridine as a catalyst. So pyridine is a heterocyclic atom. Think of it as basically like quote unquote, like benzene, but there's a nitrogen, and that nitrogen has a lone pair. It's known as a heterocyclic atom also. So this acts as a catalyst for the reaction between an alcohol and an acid anhydride if we want to form an ester. So here are the visuals, since organic chemistry is super visual. We have that pyridine, it attacks that acid anhydride, forms that tetrahedral intermediate, and then it can push out an ethanoate ion, which will leave this reactive species B, which can easily then react with an alcohol to form an ester. Next, I want to go over how we can move down from functional group level 3. I've already talked about level 3 too much, okay? So let's talk about how we can move down. So the pathway in which the reaction will go, that will depend if you're adding one equivalent, same mole amount, or an excess of an organometallic reagent. So we're going to focus on organometallic reagents. So right here's the big chart of reactions with organic metallic reagents. So if we use something like one equivalent of an organometallic reagent with the acyl chloride, then if we also do a workup, then we get a ketone. But if we add excess, then we'll get a tertiary alcohol. And the reasons for all of this I will go over in a bit. So first I want to focus on acyl chlorides and organometallics. So when we react an organometallic reagent, like Grignard reagents, with an acyl chloride, our first interaction will be the higher G electrons of the metal-carbon bond, which are then donated to the pi anti-bonding orbital of the acyl chloride. So this will eject the chlorine atom, which means that we will get a chloride ion. But if we add more of the organometallic reagent, then there will be two carbonyls that can be reacted with, which is another acyl chloride and the ketone that's formed. And in the end, we yield a tertiary alcohol. So next I want to focus on carboxylic acids and organometallics. So when we add only one equivalent of an organometallic reagent, the carboxylic acid will become deprotonated and then becomes reprotonated. However, if you add just two equivalents of the organometallic reagent, it's possible for a ketone to be formed. Next, I want to focus on esters in organometallic reagents. So, when we add the first equivalent of organometallic reagent, it will, of course, react the pi anti-bonding orbital of the ester, which ends up forming our tetrahedral intermediate as shown here. Then we have our alkoxide group. Our alkoxide group will be expelled, even though it's not that good of a leaving group due to the other negatively charged oxygen, which will end up forming a ketone. And if we add more of the organometallic reagent, that ketone will react further. And finally, we have amides and organometallics. So if the amide nitrogen has any bonds to hydrogens, then that organometallic reagent, which is either Grignard or alkylithium or organolithium, will act as a base and will deprotonate that nitrogen. But if we have no NH bonds, then the organometallic reagents will simply act as a nucleophile and will form that tetrahedral intermediate. But regardless, this will form a ketone. So right here are a few of the reactions with metal hydride reducing agents going down from level 3. Like for example, acid anhydrides, acyl chlorides. And you can see here, this is expected. Lithium aluminium hydride is much more reactive than sodium boryl hydride. So I want to talk about dival-H, diisobutyl aluminium hydride in this section. Even though dival-H and lithium aluminium hydride contain both aluminum, there are only 3 groups that are bonded to aluminium. So we get some vacant p orbital here. And a lone pair on a hydrogen, if we have like an ester here, that lone pair can be donated into that vacant p orbital. This will form an intermediate and get our acid workup here. We will get an aldehyde formed from dival-H. Next, I want to go over SN1 and SN2 mechanisms. So this is the world of nucleophilic substitution. So if we have a carbon that's bonded to 3 R groups and 1 X, so X will be our leaving group. If we have like a nucleophile, like the cyanide ion, then that nucleophile will attach itself to the carbon, and that X will just be ejected as the leaving group. So there are 2 mechanisms that you need to know for nucleophilic substitution, SN1 and SN2. So, SN1 stands for substitution nucleophilic first order, and SN2 stands for substitution nucleophilic second order. So, For SN2, the nucleophile will attack that CX sigma antibonding orbital, which will eject X. But in SN1, we get something known as a carbocation. And then the nucleophilic attacks that empty p orbital. So a carbocation is, you can think of it as just a carbon with a positive formal charge bonded to 3 other groups. So SN2 is generally for first or second degree carbons, while SN1 is for third degree carbons, because carbocations are most stable if there are 3 groups stabilizing. So then I want to go over some intermediates and transition structures. So right here, this is our carbocation. So our carbocation here will be our intermediate, and you can see it's planar. As for SN2, there's somewhat of a trigonal bipyramidal structure. So that initial bond between C and X is half broken, and we get a half formed bond between C and the nucleophile. So this is our transition structure of the SN2 mechanism. So that's it for this chapter. To be fair, I did go insane, preparing all this material, but I hope you guys liked it. So this next chapter will focus on chemical kinetics, and this will focus on the rates of reactions. So expect chapter 12 to be easier than this chapter. This chapter was kind of a fever dream. And just sit back, grab a pencil, and get ready for approximations. And on a final note, in the words of our good friend Kuravax, as stated below, kinetics is just all about solving the ODE. ODE is just ordinary differential equations, some basic calculus. As far as this book is concerned. So yeah, that's it. I hope you guys liked it. Yeah, we can just end it right here. I'm about to go insane. Okay, I'm done.
Cool.